All right, let's get started, right? So, welcome. Talk about GoChannels.net. I'm very excited about this talk because, well, two reasons. One, because I'm passionate about performance. I like to build software run fast. And I dare to say you like to do software that run slow, right? But, this is really it's going to be a talk about summary of what I learned, lesson learned, tips and tricks about a project that worked a little while ago. And of course the task was about performance, right? We have an initial application that was running about 2 million transactions per minute, which is roughly 30,000 transactions per second. It's not a crazy number. However, we knew that the application at one point could spike. They're not just talking about twice as much, but we're aiming to probably handle 10 million transactions per minute. And when you build an application that can handle this kind of payload, you're aiming to higher number. So our goal was to build an application that was able to cope at least 50 million transactions per minute. So that was, of course, an existing application. So we had a factory, but the application were actually well designed from the beginning. Was built all with the actor model built in, which is all message passive, and we'll talk about this stuff later. Anyone familiar with the actor model? Okay, cool. We see a lot of similarity between channels and actor agent, and we talk about also the difference. So the application was built from the beginning with the actor programming model, but it wasn't just fast enough. So what we did, we ended up actually to use a mix between agent and actor and channels. What we did was replace all the intra-process communication of the machine with channel. Still leverage the actor for cross-network communication. And if you're not familiar, actor comes also with a rich ecosystem that you can leverage, such as supervision, and you can build a system with fault tolerance. But channel for intra-process communication was just reduced a lot extra overhead, and the speed was quite significant. The main actually gain was not just to be able to cope with the million transaction per minute that we set, but also we saw that the CPU consumption, the CPU reduction, was about 50% less. Is that working? We were able to achieve the throughput we were aiming, but also with way less CPU consumption, which means that in the future, we're able to handle even more and more transactions per minute, right? Now, first lesson learned, we got lucky because the application was built from the beginning with concurrency in mind, right? In the end, we really just had to refactor to swap all the actor model for intra-process communication with channels. So I want to say it's easy because, but it wasn't that complex. Now, a little decoy here. Channel, we see that were designed for intra-process communication. However, we can cheat and make also cross-process communication in the same machine. There are different things you can do, like, for instance, pipes or map memory streams, sort of like share the state through memory address in the same machine. But really, it's focusing on same machine kind of concurrency. So first lesson learned, performance is not just a refactory. It has to be designed from the beginning. And if you go around, and I like when I go, meet, cross team or meet some developer, asking, talking about performance, so how fast is your application? Well, you'll be surprised how many times I get the same answer. Any guess? Fast enough, right? So how terrible is that? Because fast is not really a metric, right? It's very subjective. You don't have, to figure out your application really run fast, you have some sort of like of measure, something to compare. It's a big difference between saying my web page load fast rather than the SLA was load the page in 500 milliseconds and I load in 400 milliseconds. Okay, that's fast. You have some sort of value that you can compare. So really, when implementing a program, you have to set your performance goal up in front. Performance to be part integrated in your design, your architecture. And that's what actually really saved us when we did the refactoring for that application. Even better, like we have some sort of visual representation, visual comparison, right? Especially when you present to your CTO, your boss, the performance gain you had in your application, right? Whether it was before and after. So the goal here, the presentation, is understanding what is a communication sequential processing, which uses as building block channels. We talk about channel quite extensively. We'll see how we implement CSP using .NET. I'm going to use both C# and F#. I like C# and I love F#, but you can do pretty much what you can do in both programming languages. So I have an example in both languages. All the code samples slide are on GitHub. I'll tweet later, and actually have a link at the end that you can download the code sample and the presentation. Now, we will see the implementation in a naive way, something very simple, and then we see something more production ready. However, the production ready is a lot of code to go through in 1 hour. So I decided to start to tell you what you can do with channels. Okay? In the end, we'll see how this is implemented. Really, my goal here is give you the wonder, the willing to go back home, download the source here, how this is work, and play with that. So my name is Riccardo. I'm originally from Italy. Relocated like a year ago to Charlotte, North Carolina. I published a book about concurrency.net and Marcus MVP for about 5 years now. So why another talk about concurrency, right? Why are we talking again about concurrency? Because as time goes, software becomes bigger and bigger on demand about performance, about speed. And the reason because we have more and more data to process, right? And so originally, we can think about the divide and conquer algorithm, where you can partition your work, distribute among all the cores of your machine, it aggregates and so forth. The idea is that you can parallelize the work. However, this process demand is behind just single machine. We have to think about prepare your program, your software that is able to distribute the work not just between your cores, but also different machines. We talk about cloud computation, distributed system, and so forth. And all the idea really about still exactly the same. Partition your work and be able to run your building block independently in parallel, and found a way to glue them together. Now, the glue them together can be quite complex, but we see how channel can simplify this in an easy way and very declarative. So a good analogy about multi-threading and when you try to juggle, right? It's very easy if you try to juggle one ball, right? It's pretty boring, but you can do it. But the more ball you try to juggle on here, the more complex it becomes. And that's exactly how multi-threading works. The more thread you try to orchestrate and synchronize, the more complex it becomes. So the trick here is to try to toss all the ball in here without them make them interfere each other, okay? Same as multi-threading. But think for a second that you have a superpower. That when you have a ball in your right hand and you test the ball in the air, all the ball in the air can wait and float around your hand until you release the ball in the air, okay? Well, that's what is thread safety. That's what allows you to write a multi-threaded program easily. And channel will give you the superpower. So there are different kinds of programming models. We are all familiar with sequential one. We have one input and output, right? Pretty easy to follow. We have all the flow. The task-based programming model is more complex. Like, for instance, the divide and conquer algorithm we saw earlier. We have fork join, map reduce, distribute the work, aggregated, and so forth, and we're happy. They bring some challenge about share of state, though, right? Remember the ball that try to reach the same hand, all the balls that try to reach the same hand at the same time. The other programming model is my favorite, the message passing, which is, for example, what the actor model is based on, and we see also channel are based on message passing. And all the idea is really sharing state through communication. So CSP, communication sequential process, is not really a new idea. It goes back like almost the actor model, like back in the 70s. This paper was published and talk about how implement a CSP system that will use successfully to implement many high-performance computation. And CSP used as a building block channel, and we talk about extensively about the channel. And we see how the CSP gained more trend lately because Go, right? Go used as a concurrent programming model channel. But and the reason I think is really because channels are easy to understand, are easy to use, and really you gain a lot of performance. You achieve a great performance just with a little bit of learning curve. So in the paper, the short description of channel is a mouthful of words. It said channel is high performance, zero copy buffer, pool managed, asynchronous message pipes. Whoa. All right, I close the paper, moving on. But think about channel as a well-designed, thread-safe queue that you can use to implement a very fast, high-performer producer-consumer pattern. But what is different is that the coordination of the two endpoints of the queue is core here, right? Is what really makes the difference between other programming models. So with channel, multiple threads can share state safely and signal when one of the two ends, the endpoint of the queue completes. We see how actually we can implement this easily with built-in primitive in the .NET runtime. If you want more resources, I recommend this book Concurrent Programming in ML, which is a great resource to figure out how channels work and how actually you can implement it yourself. So the CSP concurrent programming model is really based on data exchange, right, between channels, which can be scheduled between multiple threads and run in parallel easily. So channel is really similar to think about thread workers that communicate directly to each other by publishing messages, and where channel can listen to these messages without knowing who is the sender, right? So the main operation you can perform in the channel, of course, are send or receive, or write or read, whenever you like it. And after the communication occurs, both the send and receive can proceed independently. So this follow message, though, is termed synchronous, which is still no blocking, but the send and the receiver might be exactly synchronized and agree for the communication to occur. And this is really the key of channel. So channel provide, in fact, this is called rendezvous point, right, which is a mechanism for handle concurrent jobs. Which is, again, really what makes different from the other concurrent programming model. And think about channel really designed as a building block to build your concurrent model using like a selective synchronous abstraction. Because now the rendezvous point is will wait until the receiver is going to receive a message, but also the sender wait until the receiver get the message, right? And it sounds weird at the beginning, but actually it's very powerful because there are, we'll see shortly how we can use some combinator, like the select combinator, the merge combinator, that you can use to build very, very complex other combinators. And what really gives you a great value is that in this way, you can build a very, you can build sophisticated control flow on your concurrent programs, right, without blocking, asynchronous. For instance, you can build like an if statement of your asynchronous computation, right? So as I mentioned, channel doesn't need to know how the channel will process the message later in the pipeline. What is really interesting is what channel to forward the message next to the pipeline. I really think about channel mostly like a continuation programming style, right? You do something and pass, something and pass. And on the other side, listener on the channel can subscribe or unsubscribe from the channel without impact on your pipeline, without impact how you send the message. And this is how you promote loose coupling between channels. So again, this is based on a rendezvous, point rendezvous between channels. And as I said, when a channel receives a message, the receiver will wait until the sender provides a message. But this is valid also for the opposite. When the sender sends a message, it will wait until the receiver gets the message. All right, let's start to see a bit of code here, right? So let's start with the basic here. We have the iChannel interface, the contract, the API you want to expose for your basic building block channel. Of course, we have the iReceiver with the receive and iSender with the sender API, okay? What I add here that is not really idea of the original implementation of the channel is the async part, okay? And this I did for, because in my experience, I do a lot of I/O operation, a lot of asynchronous operation. It's just convenience to have some sort of API exposed that allowed me to keep the asynchronous semantic through the program, right? So I start some sort of I/O operation, and I don't have to leave the asynchronous word as long as I need it. However, you have to be careful when you use the async part here because it's not blocking, which means that sometimes, if you're not careful, it can lead you to some nasty bug that is very hard to find. And we'll see actually an example. So this is the canonical 101 example. You have like a message passing program, right? The ping pong, where we have two channels here implemented, right? With the make, it's just an helper factory function here, create two channels, the ping and pongs, and you have two tasks that run in parallel, and we have the message passing between the two channels, so we can just echo back a message from the ping and echo back the message from the pong. So pretty straightforward, but you can see how we can start to think about this design pattern, like more complex, like many producer, one consumer kind of producer-consumer pattern. So this is a very naive implementation. I like to start simple and then build up later in the presentation. So we have like 5 tasks here running parallel that send the messages to the channel, and the other side task that actually we can use the try receive in this case. And the advantage is that we can apply some sort of flow logic here. If the message received, do something, otherwise no. In this construct I did it, but you can pass also timeout, okay? The close part here, you notify the channel that you're not going to send any more messages. And in this case, the receiver here is aware that there is no more messages that are going to be received. All right, so as default, channel are buffer, okay? I think I swapped the two. Okay. As default, channel are unbuffered, meaning that we'll only accept send if there is a receiver corresponding ready to accept the message, and vice versa. On the other side, the buffer channel, which is the construct here down here, it takes a capacity, which is the buffer size, right? And which allows you to have multiple send before even the receive is set, okay? So you can send messages without have the receiver part enabled. So in most of the time, you will use a buffer channel. It's a double-edged sword, the buffer channel. However, it's nice to have an option, like another weapon in your toolkit. I put this slide here, the code, just to show you that for the buffer channel, use like an isolated circular queue to keep up with the message to receive. And of course, we have our iChannel interface here that implements both the receiver and the sender. So for the buffer channel, this piece of code works. If it was just a buffer channel, and the unbuffered channel, it won't work. The reason because whenever you send a message here, it will wait until the receiver picking up, okay? But in this case, because the receiver is after, it's gonna stop there with the second send message, okay? That's where the synchronization happened. That's where the rendezvous point happened, okay? In this case, the program was correctly without problem, but the other side to be careful because you have the channel already enabled before sending messages. So this is a very important combinator for the channels, which is the select combinator or statement, which is core of the channel. It really provides a sort of selective communication among channels. This is how we can leverage the rendezvous point that was mentioned earlier between channels. And the select here really enforces you that only one thread, enforce multiple threads to access the shared state one at a given time. Of course, it's not deterministic because every time you send a message, really you don't know which channel going to hit first, but you still have the advantage here to be able to have like a thread safe logic in place. Think about channel select as a task anywhere. Are you familiar with task anywhere? Okay. Similar, but more powerful, because in this case, really we can apply some sort of target behavior on task notification, right? We can really apply the specific behavior on the specific channel that notify the message. So semantically, also you can write really almost like a switch statement on task, on channel, right? We have our select here in different kind of cases, and then we send the messages, and the channel corresponding that pick up a notification apply a different logic. Here, just all do the same thing, but you get the idea, right? A different kind of logic. And we can further, you can see how we can use this simple combinator to build something more complex, like a multiplexer or a fork join pattern here. We have the many receiver here, an array of receiver that all send a message to the sender, one sender. We apply some sort of projection here. So whenever we receive a message, apply the projection and send the result to the sender channel, okay? It's nice we can build just in a for loop here, for instance, apply all the subscriber channel to the same instance, the same select. And the select also gives us the power to build other combinators, such as the merge combinator, which what it does, well, when you have a set of receiver, right, or channel that receive a message, they all can be combined together and work like as a single receiver, like as a whole, as a receiver. This is actually quite convenient when you build some sort of like a singleton pattern between channels, for instance, like a login, right? You have multiple logs of your application, you send to a single point to the login, right? And the same concept can be applied to build patterns such as the multicast channel that you can just have a class that you can use to subscribe on a subscribe channel, right? It really won't impact the logic. It just get the message notification and send the notification to all the subscriber, which is kind of quite convenient, right? A little more complex here, again, just using simple combinators such as the select, merge, and so forth, we can really build something a little more complex, such as the pub and sub channel here, class here. The idea here is that we can build some sort of broadcasting pattern, right? Your application, such as you can dispatch the notification to all the channels that register the subscribe here to your object in your application, and be also share among your application. One use case here is, for example, channel are built using a type construct, like a generic type. It can be a channel of T, can be anything, string, person, object, whenever. But you could eventually apply like a topic of the channel. Channel that take a string, okay? They can be differentiated in this kind of pattern, like a broadcast pattern. So now you can almost create like a mini Kafka in your application. So you send a message to the channel, they all match the same topic. So a message broker, if you're not familiar, it is a literally a pattern, like an architectural pattern that enable application and integration via message-driven paradigm. And in this case, channel are just a perfect fit, right? We see how we can really easily decouple the application, which is a central concept when you build concurrent application. Okay, we have actually used the merge here, and what we can do now, we can treat the notification of the channel also like almost an enumerable, right? A range. And what we can do here is that treat the channel or the notification as a sequence, right? And for this exact reason, we can treat the channel as like links, we can write link semantic around your channel notification, right? And for that, we can apply all sorts of like high-order operations, such as map filter, and apply that high-order operation to the content of the channel. So for this reason, we can apply, some sort of, this is very naive, but link operator on your range, and treat like events as an enumerable, or even convert to an observable easily, and apply all sorts of reactive extension high-order operation without blocking. Any questions so far? All right, so, oh yeah.
So channels are completely open memory. You never worry about a channel that might bridge between PCs, but maybe between processes. And when you're bridging between processes, does the memory get copied into the channel and outside the channel as it enters and leaves, or is it like a span or something?
Well, so it depends. You have two options there. When you do cross the process, you can use low-level memory address. So at that point, it won't be copied. Right. Okay. On the other side, that probably is my favorite. It's not really high performance the memory share, as I said, but you can build a system that creates actually an isolated binary file, so it can be crossed. And the reason because I like the file is one for debugging, one because you have multiple processes, not just two. It just gives it a bit easier. Probably I will build the share across process using the file and then swap it with the map memory. And they both use the same API, okay? One use a stream and one use like the memory map, but you can do both. Does that answer your question?
Yeah.
Okay. Okay. All right, so it seems like channel and actor or channel agent are very similar, like have a lot of commonalities between the two. So briefly, what is an agent? Well, think about an agent as a unit computation that is single-threaded and is built by three main components. A mailbox, where the sender sends a message, asynchronously, no blocking, to the mailbox, which is pretty much like a queue. And because it's single-threaded, the agent will just run one single thread, is thread-saved per nature, right? There is a behavior, which is the function that apply a projection transformation on the message received in the mailbox. And the agent pick up one message at a time from the queue. And the projection, the behavior, apply the projection for one message at a time and can either or not update the state, which is isolated and protected by the agent itself, which means the state can only be accessed by the agent, okay? So it's still based on the message passing programming model. But there are some difference between agent and channel. So agent are, well, no agent actor come with a rich ecosystem, as I mentioned earlier, that we're remoting for cross-network communication, supervision. Channel don't have that. However, channel are very much composable. Like the one of the strongest part here is composition. The fact you can compose channel easily. On the other side, agents are very hard to compose, right? Because you send a message, or you can send or you can ask for a message. You send and wait for the response back. But if you try to do some sort of control flow on your concurrent program, cross-network, this can be like a pain. On the other side, agents, besides the poor composition, are unbounded, right? Which can lead to some memory issue if you're not careful. Channels are built with the idea of, the rendezvous point. They try to be sure that you're not running this kind of issue. Of course, you can use the buffer channel, but the default construct is the unbuffer. So really great channel, great for building control flow on your concurrent program, and definitely speed. The performance is a big plus here compared to the agent and removing all the extra overhead. And talking about back pressure, agent or actor, they're not really designed with back pressure in mind. Any familiar with back pressure? So back pressure is when the consumer run at a higher speed than the producer run at higher speed than the consumer. So the producer can overwhelm the consumer. So you have this called back pressure when the consumer tries to cope. And there are many different kind of technique you can overcome this problem. But channel, with the fact again with the rendezvous point, is pretty much built in the idea that you don't have these issues. So this is a naive implementation of F#, and I like F# because I can put all this bunch of code in one slide. But because the commonalities between agent and channel, we can build a very simple naive implementation agent using F#, which has a built-in agent called the mailbox processor, okay? Right here. But I like to start with this naive implementation because we'll see later how this high-level idea apply also to more sophisticated implementation. Right. They all use a sort of 2Q inside the channel to coordinate reader and writers, okay? So in this case, I have a message type, the channel message in top, which take the two type receive or send. I expose my asynchronous API, receive here, and down here the send. But when I receive the message, I can use the agent, which is run a synchronous no blocking loop here, to get the message and then pattern match. Either can be received or sent, and then what I do in the logic is I check. If there is some writer, when I receive a receiver, I check there are some writer. I proceed with my channel communication, otherwise I'm gonna queue up the writer in my local queue. This is this channel actually is unbuffered, so you have to be careful about memory, but to give you the idea how easily you could implement a channel. We'll see how we can do the same thing in C# shortly. So channel composition pattern, which is really the core about channel. I'm gonna go just gloss over here, so we're gonna jump in some code example. But the idea you can implement many patterns from the channel pipeline, which is the idea that you have some sort of complex system that can be designed in multiple steps. And each step do a computation and pass the result to the next step of the pipeline. The main goal here is when you have the step in a pipeline, they'll be able to load balance the work between steps, okay? So this is used, the agent channel implementation just show you 2 slides ago. We can implement a simple function here that take a projection, take type any type A, and produce a computation async, can be a task in C#, and take our channel. And what we do here, we have an asynchronous computation that run in loop here, with a recursive loop here, run asynchronously. And what it does, it receives the message from the channel, apply the projection here, which is up here, and pass the result to the channel, to the next channel of the pipeline. And here we can implement easily, for instance, image processing, right? We create a channel, which has to pipeline it. We load the image, the result is passed to the next channel, and apply some sort of 3D effect to the image, and then save it, and so forth. So we have this very declarative way we can pass the result of the channel in a pipeline. A little bit further, F# doesn't have C#, with the fact the function of curry by default, which allow me to write this function called point free. It's just a fancy word to say that function F#, you don't have to pass all the argument. You can omit, for instance, the last one, and the compiler infer that this is a function that take the missing argument and return a new function. By this way, we can implement point free function and use this pipe operator in F# to declarative pipelining our computation, in our chain computation. Easy to produce, one producer and consumer. A pattern that I use all the time is when you have end producer and end consumer. You get a singleton. We saw this a bit with the merge, for instance, with the login. We have fork join pattern, map reduce, and so forth. Many patterns you can implement with channel easily. Anybody familiar with the TPL data flow? Okay. So the TPL data flow was designed really to build this workflow using building block. You break your program in small components and you pipe them together, you link them together. So we can leverage the TPL data flow to implement a sort of agent in C#, which is not built in, but we can leverage the three main components of the agent, which is state, which we can define here in a constructor, the initial state or the agent. We have the behavior, our projection, to take our state, take the message received, and return a new state. And then we have the mailbox. In this case, we can leverage the TPL data flow action block. And this is the secret line of code to implement a channel, an agent in C#. We just receive a message here, apply our computation, and update the state. And because it's single-threaded, is fine. So this is the code, pretty much mimic what we saw in F# here in C# using the agent as a construct. And again, here we have the 2Q in top as coordination between reader and writer. I'm going to speed up here. So I'm going to pass the code. I'm going to jump here, and then I'm going to run all the demo until the last. So anyone familiar with trading channels, actually? Microsoft. So it's a bit different, but very high performant. So Microsoft introduced this last year, June 2017, and is part of the system trading channels namespace. It ran the full framework 4.6 or .NET Core 2.0. So the library provides really high performance producer-consumer pattern, still with a rendezvous point idea, still the synchronization point, which mimic very, very close what Go channels are in .NET. We have an example here for streaming. I'm going to show you later, just live streaming from my laptop here, do some sort of string manipulation of the image, and push it to a browser. We're going to see the example, how easy it is to implement and how nice. The API of the channel, pretty much similar. It takes a construct based on channel, class, and it returns two properties that can be used both for input and output. The readable channel for output and the writable channel for input. You see the API also exposes the async part right here, which is quite nice. For instance, the wait to read async here, you can see return a Boolean, which can be used like in a for loop to wait that one message is available. And I think this is going to be awesome when in C#8 we're going to be introduced the asynchronous stream. This is going to be fantastic. There'll be two types of channels as well, unbounded and bounded. Same concept before we talked. The idea though, there is some property here you can set also how to handle back pressure, wait for channel, drop some channel, and so forth. That's it. That's how you use it. You create an instance of your channel here, up here, create a bounded channel, and then you have multiple tasks. This is like, for instance, many consumer, one producer. You have like many threads here running and waiting to receive a message using the wait to read async API, which is blocking the flow, but not the threads here. The threads still turn to a scheduler. Wait, when it's available, read the message and do some computation. Just run the console here. And here you're going to push the message you write to the channel, the message, okay? All right, so let's run the demo here. I'm going to run the opposite. I'm going to run first the .NET channel, and then I'll show you the implementation of the channel that I built. All right, so this is a summary application. They use macOS. I'm going to grab my local web camera here, transform the buffer in an image, the buffer byte rate in an image, and then push the image in an image to ASCII art, which is a very fancy function that what it does it transforms the image in shade of gray. And for this shade of gray, apply an ASCII character. And here I'm going to rebuild the image in a string format. On the other side of a server, we use SignalR in two versions just for fun. Any familiar with SSE, server-side events? This is awesome. If you're not familiar with SignalR, it's a bidirectional communication between client and server. However, there are many cases when you have a just one-way communication from the server to the client. For instance, update a dashboard is a great example, right? And this was designed really performance-wise for this kind of scenario. So I use both here just for fun. The idea here, I get my channel here, create the instance of the channel for each of the client register to my browser. I pass a connection ID, which is unique, and I use a local concurrent dictionary to keep track of the connection ID and the channel. When the channel receives here, it's going to push the result to the browser, where here I use this API to send from my from the video streaming the client to the server. All right, let's run it. Just run it because it's fun to run this guy. All right, so browser is up and running. Hello, okay, run the stream here. So you can see how easily you just have really a big, nice, fast producer consumer. Whoa, hello everyone. And here we have the ASCII format, right? And channels are here. Performance-wise, very similar because if you didn't know, actually, SignalR is built on top of radio channel. Kestrel, am I familiar with Kestrel, right? Super high performance server. Well, use I/O pipelines, which are built on top of channel, more specific for I/O operation. So you can use this stuff today, and I really recommend it because they are just lightning fast and are easy to use. Any question about this part? You can see my drink water, okay? All right, so, yes?
How often is this synchronizing, or is this matching the frame rate?
I think I put like 30 flaps. Okay. Yeah, but yeah, you can do higher, lower, whenever. So, good question. And you can download this code example here. This is our use summary, so run on Mac, but the idea you can convert in .NET Core easily, right? Actually, use .NET Core pretty much. All right, so hello, stop this guy here, kind of freaky to see myself. All right, so I'm gonna run a few examples here. I'm gonna run one simple, and then we're gonna jump to one more complex here. So this is the source code you can download. There are a few implementations of the channel. The channel async, the one that I use most of the time. Channel implementation is here. Make it zoom here. You can see use a different kind of queue node here. I'm not going to go in detail here because it's a lot of code, but I really recommend to go home, download the code, and play with that to see how to implement underline. I'll just give you the wonder how all the cool stuff you can do with channel. So this is going to be a simple demo here, but there is a gotcha. No, this is the agent channel. I'm not going to show you. Well, let's run it. This is the agent channel that I was showing, implementing using the TP data flow and channel, okay? The idea is you use some sort of 3D manipulation, passing an image here, which is in our data folder. For instance, we have some dollar bill here, and then we have Geneva, of course, the classic example. Let's run this guy here. Let's run it, and that's gonna be passing here. Oh, output. The output is going to be here, hopefully soon. Okay, we start to have the images pass, and you can see apply some sort of 3D here. But the idea how you can pipeline, create your channel, and pipeline the channel for the computation for the image processing here. The other example I want to show here is the tricky one. Let's see who can tell me what's going on. So this is the buffer that I will show you in the slide, right? Now, I'm not going to run it right away. I'm going to make a change here. Let's put channel here, remove the buffer. Okay? Now, what do you think is going to happen now? If you pay attention to my presentation, you know the answer. What do you think is going to happen? Gonna hang? Anybody say gonna hang? Anybody say not gonna hang? You know, that's a tricky question. You know that's not gonna hang. Because, let's run it. Yeah, it's set correctly. Run. Because that's exactly when I was telling you that when you use the async API, it can be tricky. It works. Theoretically, when you run this piece of code, it should hang here because the receiver is not set. But this is a task. It's not awaiting here. So to fix the problem, you should put await here. Of course, change your class here to be async task, right? And most likely to remove this guy here. So now actually is blocking because that point was just returning a task. So it was not really blocking until the computation was completed. So at this point, if I run it, it's gonna hang after the first send async, okay? And yeah, nothing gonna happen, we can wait there. How to fix this? Well, we just move the async part here after the task, for example, or use the buffer channel as was before. But now if you put the send async after, this is going to run correctly, okay? Well, perfect, okay? All right, 3 minutes to go. I'm gonna run this example here, which is the example here is just like a multi-search in a file system. What it does, we have a channel for search engine. They broadcast the search for any Finder channel that you're looking for, and then you write the result to the ultimate channel, sort of like fork join result pattern. What is cool here is that it can be easily parallelized here. I have a data result here, which is our output here. We have a bunch of text here to look into, okay? I created 2 channels, the file writer, which is just below here. Just write the result, wait to receive the message, and write the result to the local file system. The search channel is where I set my search parameter, like the text type, the file type, and what I look in this file, and then send to all the channel for each file to broadcast to all the channels that are listening, okay? In this case are defined here with the word finder channel. I just create 4 instances here and gonna be all running parallel, okay? So let's run this code here. Let's actually be sure, delete this file here. Let's run this guy. All right. All right. File pattern, well, they all gonna be text here, of course, and let's look for dog. All right, already done. Let's search for another content here, in this case, cat. All right, done, and we'll see the result here to refresh. Okay, and here just see how fast was it to search to the file system here. I find the file that contains the dog, give you the line here. All right, that was actually simple pattern, but you can see how you can leverage channel to build a small application. All right, I have 1 minute to go, so I'm gonna just post here, open for question, and here we talk about CSP, talk about channel, a programming model. We see how different implementation, C#, F#, both the code sample beside the video stream are in a code that you can download are in F# and C#. I did a 101. Channel can be composed. The channel here actually can dispatch over 20 million messages in seconds. So take a look about this cool technology. It's fantastic. This is my information. I/O channel, I'm gonna tweet later when it's ready. I didn't post the slides yet, but I will do it with the last changes. But take a look maybe later today, the branch here, the repository there. This is my information. And question? Yes?
How do you debug your system to make sure you get your buffer levels set to the right level so you don't have those backrush problems?
Oh, this is a very good question. So, first of all, what I do is you can use. There is not really good way to do it. The only thing I can think here is some sort of login built in that would give you the thread ID that you can use. Like, are you familiar with the concurrency visualizer? There's a plugin for Visual Studio. It was there until 2015. Then you have to now add it separately, but it's fine. And give you how all the threads work. So you can give like, I think there was, maybe I remove it, but you can give a name for the channel, like for the task, and you can map that, how does it work. But you have some sort of counter. Actually, there is a code example there in the show that it shows how you can implement a counter for the channels. So you can keep track of that many receiver and many sender. Right. Any other question?
What's the name of your book again?
Huh?
What's the name of your book again?
Concurrency.net. Yeah.
When was that published?
It was published a year ago, July last
Does
year.
it have system.thread.channels?
No. That was published pretty much. The book was published when Microsoft. Yeah. I have the channels are not covered in the book. There is actually chapter 13 is my favorite. It's pretty long, but it's a bunch of recipe for different kind of concurrent problem. And one actually talk about channels, which is only like 5-6 pages, but it gives like how implemented, why it's worth it. Yeah.
So if we're going to be implementing channels, do you still think we need to roll it out, or is something like the Microsoft implementation good enough?
So the main difference that I can see between the two is that one is implemented really with a high performance produce and consume on steroid, the channels Microsoft. The other one gives you more flexibility for the composition aspect, right? Because the Microsoft one, you really have like write something and read something. The other implementation, the channel, you can read and write, but also you can compose them. You're more control, right? You build it yourself. It would be interesting actually to mix the two things. You abstract away the Microsoft channel implementation with the other channel. Actually, that's going to be good. Accept, pull request if you're interested. That's a good idea. Yeah.
Can you show that first slide with your book on it, please?
Yeah. Here.
Thank you.
Sure.
Is bounded the same thing as buffered?
Yeah. So I was saying actually that the original CSP implementation used buffer and buffer. Microsoft used unbounded bounded, which very much is the opposite, right? Right. But watch out. But the constant won't lie. One take capacity and integer, one doesn't. Cool. I really hope that you give you the wondering. I think it's a very cool technology to play with that, especially if you're like a performance junkie like me. I'll be around. I'm friendly. I won't bite, and I'm always happy to, if you buy me a beer, it's good.